the important question of the day is, what does multiplication mean? If you could think about that for a moment. And as when we look at addition and subtraction meanings, a physical example is a good idea for multiplication. What does it mean? Multiplication means, what do you got, Matt?
I got a shortcut to show the operation of addition by combining figures.
All right, shortcut for addition. Example?
Oh, like you wouldn't say 2 plus 2 plus 2 plus 2, it'd be 2 times 4.
Okay, cool. Anyone else?
Pretty much.
That's what you had too?
I said taking two or more numbers and doubling them in a
Okay.
way.
Doubling numbers is multiplication. Yeah. What was that, Isaac?
I just did the expansion object by set.
And by set. Oh, that's a good one. Do you have an example? Okay, so I was thinking something like, what I would do for an example of that would be something like have 4 groups of 2.
Yeah.
Right, so I have a group of 2, and I'm expanding by set amount 4 times. So 4 groups of 2, thank you. So here's a group of 2, and here's another group of 2, and here's another group of 2, and there's another group of 2, and so that would give me 8. Yeah, which is again like repeated addition, right? Which makes me think, if this is 4 groups of 2 down here, should this be 4 times 2 instead of 2 times 4? Because isn't this 4 groups of 2 up here?
But it doesn't matter.
It doesn't matter whether it's 4 times 2 or 2 times
When
4.
you're multiplying, yeah.
So
this is
Eight either way.
in this instance, without any labels, it doesn't matter.
okay, without labels, it doesn't matter.
There
But
could be 2 groups of 4.
but yeah, 2 groups of 4 would look different, right? So here's 4 groups of 2.
If you wanted to relate it to the bottom example, then it should be 4 times 2.
Oops. Yeah. So in some sense, so you get into the idea of multiplication is commutative, right? It shouldn't matter the order you multiply in, and we got used to that growing up. But when we model it, it turns out it kind of does matter.
Usually word problems will have examples that'll give you labels that make your brain put it in the order that's in the problem.
Like this right here, this picture right here would be 2 groups of 4. Now the answer is the same. There's 8 things in the end, but they're 2 different scenarios.
Couldn't you theoretically see the 4 groups of 2 as 2 groups of 4 though?
Yes, theoretically you can,
Seeing that now.
but yeah, but physically they're different. Yeah,
Yeah.
theoretically they're the same, physically they're different. Is the point here.
If you were
If you were to like circle the top row and the bottom row.
Yeah,
of
you could regroup them.
Same thing.
But if you were
And it's
doing
the
a word
same
problem
amount.
and you said there were 2 families of 4,
Yeah, that's different than
Yeah.
4 families of 2. Yeah. So it depends on the physical situation, but theoretically you are correct. Multiplication is commutative, meaning the order of the multiplication leads to the same product, which is cool. All right, anybody have something different? We got repeated addition, we got groups.
opposite of division.
Opposite of division, we'll get to that later when we get to division. That is certainly true. One that comes to mind for me is I do a lot of construction on the side, and so I'm regularly having to figure out areas. And area is length times width. Or perhaps base times height.
The formula a bit more complex than a simple definition for multiplication. More specific, at least.
The general way we calculate area is based on squares.
Right, but I'm saying like your example versus a definition for multiplication.
My point here is I believe area can be a definition for multiplication. So if we view area as some base, like let's say a base of 4, and I measure out 1, 2, 3, 4. Let's cut off the excess, and a height of 2, and so I measure up here 1, 2. Then in terms of the way we measure in squares, square inches, square feet, square centimeters, square miles, things like that, then I definitely have 8 square units here.
My point was that you can use multiplication to find the area, but that's like saying, asking someone to define colors. And they define it by the spectrum of light that your eyes can identify, and then saying colors are blue, if blue is a color, which isn't incorrect, but also it's not.
Blue is a color.
I understand what you're saying.
Yeah.
But like, it seems too specific for the proposed question themselves.
Yes, I hear what you're saying. So my answer to that is in the world around us, we tend to differentiate between continuous and discrete things. So discrete are individually countable things. Individually countable. Example of individually countable things would be like fingers or pencils, or I'm counting my sheep, things like that. Counting students in a class. Versus which the previous examples are discrete examples, because I have these individual objects I'm grouping. In this case right here, I'm dealing with an idea called continuous. And continuous isn't necessarily discrete things, because I'm thinking continuous is like paint.
Right, you could alter the formula's numbers to make it perpetual.
And painting something is a little bit different than counting individual objects. Like we don't count pieces of paint necessarily. So this is what we call the area model for multiplication, what we call a continuous model for multiplication, whereas the groups of repeated addition idea here is a discrete model for multiplication. Is kind of the way I like to think about that. But then we get the whole chicken and the egg thing. What comes first, multiplication or area?
Egg comes first.
Yeah. So that's a tough one for sure, philosophically.
I understood.
I agree with you on that.
particular conundrum, but
Yeah.
I understand your example.
Okay, cool. So we've got a few different models right now. So I'm just going to number these. Oops, wrong direction. Coming back this way. Let's say our repeated addition here is model number 1. This over here, let's call that model number 2. And I like to call it the groups of model for multiplication. It's a set model for multiplication. And our model number 3 here is the area model for multiplication, which is a continuous versus discrete model. It's not discrete, it is continuous.
What was the name of the second model?
The second model I call the groups of model.
Okay.
And it is a set model.
Thank you.
Other models that we have for multiplication are, let's see, model number 4, it's called the Cartesian product. And the Cartesian product is about matching sets of options. And this is related to an idea we talked about in problem solving and set theory. Where suppose we have, like, we're going to get a car, and for the car, we have certain types of options. And so one set of options could be color. And maybe our set of colors are red, green, blue, and white. And then we have, say, options about the engine. And the engine is either gas or electric. Then what are the different possible cars that you could come up with? And there's several ways to go about illustrating that. One way is to just say, you can branch out for the different colors, red, green, blue, and white, and then each color is either gas or electric. And then in the end, I can see that I could have a red car that's gas or a red car that's electric, a green car that's gas or a green car that's electric. But in the end, these 4 options by 2 options end up giving us 8 options in the end. And earlier I called this the fundamental principle of counting when we were playing with sets in problem solving. Another way to graphically illustrate that idea of a Cartesian product is we could label colors here, red, green, blue, white, and we could label gas versus electric down here. And then we end up with these combinations, red gas, red electric, green gas, green electric, blue gas, blue electric. So kind of like graphing points. And they're all these models are related in a sense because they all represent multiplication. But like here with the second version of the Cartesian product, that looks like 4 groups of 2 or 2 groups of 4, depending on your perspective. But it's one involving choice. And just one more note back to the groups of, when we draw the groups of in a grid like this, some people call that a whole different model. So I'm going to throw in a 5th model here. When you make a grid out of the groups of like this, so here I have a 4 by 2 grid, that's referred to as the array model for multiplication. But the groups don't have to be nicely laid out in a grid. We potentially have 5 different physical ways to demonstrate why 2 times 4 should be 8. And they all are consistent, they all agree with each other, which is important for something like this. Now, based on those models, all kinds of interesting things happen after that. So properties. So one property we already talked about is the idea of commutative. Remember, the word commute is in here, and commute means to move. So that's the idea that 4 times 2 has the same result as 2 times 4. They have the same product. result of a multiplication is called the product. Does anybody know what the things you multiply are called if the answer is called the product? Not variables, although they can vary. Not numerator, that would be we're playing with division. They're called factors. So 2 and 4 are factors. They're factors of the product 8. And I want to get some toys to talk about the next part. Let's see. Find color rods. Search term. All right, so with the associative property, we have 3 numbers we're multiplying. Multiplication, by the way, is what we call a binary operation. You can only do 2 at a time, right? You can't do 3 things at once. So either you're going to say 2 times 3 is 6, and then 6 times 4 is going to be 24. Or you could say 3 times 4 is 12, and then 2 times 12 is 24. But bottom line is I can only do 2 numbers at a time. And the numbers didn't move. I didn't move the 2 or the 3 or the 4. They stayed exactly where they were. I just choose to associate them differently with parentheses. Right? So this is different than the commutative property. So I want to look at this with the color rods. So with the color rods, the first example says I have 2 groups of 3. So 1, 2, 3. There's one group of 3. Here's another group of 3. And then I want 4 groups of that. So there's another group and another group and another group. So this shows 4 groups of 2 groups of 3. Looking at it the other way, I've got to show 3 groups of 4 and then 2 of those. So here's a group of 4. And let's say I want how many? 3 of those. And then we want 2 of those. Oops. And then the question is this really the same amount of stuff? Could I rearrange one to match the other? Any suggestions?
You turn the bricks at all?
I can't rotate them here. I can only move them around. So I can't make them vertical instead of horizontal. What if I look at 3 groups of 4 in the other direction? So make the 3 groups of, 3 groups of 4 go that way. There's the other 3 groups of 4. And now you can see they match up. They're the same size and shape. Okay. So that's one fun thing about toys like this is you should be able to justify these properties with them. Add that to the notes. All right, so there's a physical example. The top one shows 2 groups of 3 4 times. And the bottom one shows 3 groups of 4 2 times. Demonstrating a physical version of the associative property. Multiplication has a couple of things that are different than addition or subtraction has. So like addition and almost subtraction, we do have an identity property. Identity is when you multiply, but nothing really happens. 0 is the identity for addition, 1 is the identity for multiplication, right? 3 times 1 is still 3. We didn't change the identity of 3 by multiplying by 1. Similar, we got 1 times 3 is also 3. Right, so 1 is the multiplicative identity. Another property like addition is closure. Anybody remember what closure meant? Closure means the answer is the same kind of number that you started with. So it's closure, R there. So in this case, closure means the product of two whole numbers. Is still a whole number. Now, multiplication, though, gets a little more interesting than addition. So addition had similar properties: commutative, associative, identity, closure. We've got this really weird whole number called 0. And multiplying by 0 is bizarre because 0 times anything is 0. And nothing like that happens with addition or subtraction. So 0 is its own special property in multiplication. Anything times 0 is still 0. And unfortunately, this causes a problem with division that we'll see later. Another cool property is when we mix multiplication and addition together. It's called the distributive property. Now, it turns out there are several distributive properties. So more specifically, the distributive property is really called the distributive property of multiplication over addition. And I like to use the area model to demonstrate this. So I'm going to draw a grid. And I'm just going to break up the grid a little bit by making a division right here. So here I have 2 and 3 to get the total of 5. And then the height here is 2. So I have two ways of looking at this rectangle right here. I can look at it as a 2 by 2 area combined with a 2 by 3 area. Or I could observe that the whole base here is 5. So that's going to give me the same thing as 2 times 5. So the distributive property as an area model, it's always too tall. So this would be the problem 2 times parentheses 2 plus 3. Which, thinking about the order of operations, is really 2 times 5. Or, right, we have this idea about distributing the multiplication over the addition sign, we could view it as 2 times 2 plus 2 times 3. Either way, I can get 10 on it. So the distributive property is a consequence of what multiplication means. You could say it's a consequence of being repeated addition, or you could say it's a consequence of an area or an array of things.